Hello, my name is Robert Smith, and I'm with New River Community College, and today we are looking at the octet rule. We're looking at some exceptions to the octet rule specifically. We're asked to draw the Lewis structures for the following molecules and ions. We have aluminum oxide as our first one. So if you recall the formula for aluminum oxide or want to just solve it using charges, it's Al2O3. And so what we're dealing with here is there are exceptions to the octet rule. Aluminum is one good example of it. The atoms that do not want 8, they want only some number less than 8 electrons, include hydrogen, helium, lithium, beryllium, and boron. Aluminum does want 8, so does oxygen. But can we satisfy the 8 using simply the electrons we are given? Such is not always the case, but let's see. So if we were given this particular molecule, the structure of which would probably have an oxygen, 2 aluminums on either side, and maybe let's put an aluminum over an oxygen over here and an oxygen over here. That's roughly what it looks like. Not necessarily true, but you'd have to do a little experimenting with it. Oxygen is not going to want to bond with another oxygen per se. It'd much rather bond with that aluminum because of its metallic nature, because this is a metal and a non-metal. This is an ionic structure. So what we're going to do is we're going to look at the formal charges on this. This is a little more complex than our previous ionic compounds. So we're going to look at this in terms of just treating it as though it is a molecule rather than an ionic compound. So for aluminum, we've got 3 electrons per unit. And with oxygen, we have 6. So let's just go ahead and put those up. Okay, for a total of 24 electrons. Now let's just, for the sake of reasoning, go ahead and take each aluminum and give it a single bond. Put it over here, let's make another single bond. Just going to do a very simplistic version of this. Okay. And we don't like lone pairs, so let's just go ahead and get rid of some of those. Didn't want to erase the oxygen, but we're just going to make a double bond there. And let's get rid of the double bond here. Go. Now let's count up the number of the actual species we have here now. We've got, or a number of electrons rather. We have 4 on each of the oxygens, so for a total of 12. We have a double bond to each oxygen, so that's another 4, so that's 8 per oxygen. 8 times 3 is 24, so we still have the same number of electrons, They're just formulated in a different fashion. And we can actually calculate the formal charge on any given one of these and determine that this is in fact the correct structure. There may be an angle difference, and there probably is, but let's just go ahead. In fact, we kind of know what the angle difference is. So let's redraw this using those same lines, same bonds, except maybe a little more accurately. So we would have an oxygen with two lone pairs bonded, much like water is bonded, at that bent kind of angle there to two aluminums, who in turn are double bonded to an oxygen, which in turn has two lone pairs on them as well. So that's more what it looks like. L looks terrible. The whole thing looks pretty rough. Anyway, okay. So to calculate the formal charge on this, to make sure that we've got the most stable conformation, let's start with, actually let's change that over. Start with aluminum. Edit. Calculate the formal charge on this. Let's start with aluminum. Aluminum has 3 valence electrons, and each of the aluminums, none of them have any free electrons. And there are 3 bonds, so the formal charge on aluminum is 0. For oxygen, we have 6 valence electrons, and there are 4 free electrons on each oxygen, and there are 2 bonds on each oxygen, which also gives us a formal charge of 0, which would seem to indicate that this is in fact the most stable conformation of aluminum oxide in this particular case. Because aluminum, while generally speaking a metal, it is a metalloid, and it will behave as a non-metal sometimes, and this is one of those occasions where it will behave like a non-metal in the forming of these more direct Lewis structures, rather than it just being a very basic cation anion representation. Diphosphorus pentoxide is our next one. Again, this is a little complicated because we're dealing with phosphorus here. Phosphorus is third period. Whenever you see third period, you got to think there's a decent chance that I'm going to be violating the octet, especially when there's 5 oxygens going to 2 phosphorus. So let's take a look at what we're going to do here. Now, we've got, let's just do 1 oxygen, and we'll do another oxygen over here, and 1 over here, 1 over here, 1 over here, and let's put a phosphorus and a phosphorus. Okay? If we were to say that this is the proper representation, and again, this isn't something that you would pull out of thin air, although it seems I've just done that now. It takes some time in recognizing. So the way I'm thinking about it is in terms of formal charges here. So in order for oxygen to be at a 0 formal charge, the likelihood of it having a double bond and 2 sets of lone pairs is pretty high. Because if you look at the formal charge of oxygen, you got to get rid of that 6 valence electrons. And you can do that by either having 6 free electrons and no bonds, but then it's not exactly part of the molecule anymore. Or you could have theoretically 6 bonds, but that doesn't work. You can only get up to 3. And electrons don't like to be single, they like to be in pairs. So you're pretty limited on how to make oxygen into a zero. So the easiest way is to make it so that there are two sets of lone pairs, which means 4 free electrons and 2 bonds. Okay, so that means that we're going to want oxygen double bonded to phosphorus at any given location, either double bonded or 2 single bonds, as is the case in the central. Now, assigning the oxygen the other electrons is relatively easy. And this is significant because phosphorus is a group 5 element, so it should have 5 valence electrons. There are 2 of them, so that's a total of 10 valence electrons from the diphosphorus component. And then pentoxide, oxygen has 6 valence electrons. There are 5 of them, so that's 30. So there should be a total of 30 plus 10, which is 40 electrons. If we count these out, each double bond counts as 4 electrons. So we have 4, 8, 12, 16, plus 2 sets of single bonds, that's another 4, so that brings us to 20. Then we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 single electrons. 20 and 20 is 40. So we've used up all of the electrons in this particular Lewis dot structure. And we can even check the formal charge of phosphorus. So phosphorus starts with 5 valence electrons. It doesn't have any free electrons, but it does have 5 bonded electrons. Therefore, its formal charge is 0, and this is the correct Lewis dot structure for diphosphorus pentoxide. Now let's look at the carbonate ion. We're going to do a little resonance on this one, just so that we can see the change in which one stays a double bond and which one goes to a single bond and so forth. Carbonate is CO3 with a -2 charge, which gives us a total of 4 electrons on carbon, 6 for the oxygen times 3, because there's 3 oxygens, plus the extra 2 gives us a total of 24 electrons. So we're going to have carbon, and then an oxygen, oxygen, and oxygen. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 electrons, and that's how we make our stable carbonate ion. So we got a -2 charge on it. And we can, of course, draw the resonance for this, wherein we have this double bond breaks up. This one comes over. Then we've got this carbon, oxygen, and then, of course, you have the next step, which would be this, going over here, and that coming down there. And then the third structure. And this one would have our arrows going from here to here. And of course we have our arrows, double-headed arrows, showing the interchange of the resonance. Okay, last one, sulfur hexafluoride. Again, we're looking at the octet, but we're looking at it in terms of when the octet applies and when it doesn't apply. And sulfur, again, third period, you see 6 fluorines and 1 sulfur. There's no way that sulfur can stay at the octet and stay stable. So we need to have 6 fluorines on the octet, on the sulfur, which violates the octet. But because it's period 3, it's okay. People get so hung up on the octet, but remember, octet applies preferentially to most molecules, but exclusively only in period 2. So, how are we going to draw this? Well, fluorine only likes to be singly bonded. So, we're going to have a central sulfur. We're going to have 1, 2, 3, 4, 5, 6. And that fulfills our need for SF6. Sulfur falls in the needs of 6 valence electrons. So if we were to do the formal charges, sulfur has 6 minus 0 free minus 6 bonds, which gives it a formal charge of 0. Fluorine has 7 valence electrons minus 6 free electrons minus 1 bond, which also gives it a 0. It's quite satisfied. Now, if we were to add all these up, 7 times 6 is 42, plus 6 is 48. So let's count up everything, make sure we have all of our electrons in place. We have each of these bonds counts as 2, and we have 6 of them, so that's 12. And then we have 6 times 6 free electrons, so 36. 36 plus 12 is 48. So therefore, we have used all the electrons that we need, and our Lewis-Dot structure fulfills the requirements of using and accounting for all the electrons and having the most stable formal charges. So that's a little bit of the exceptions, the octet, and some of the odd things you might come across in creating Lewis-Dot structures when you, and the follies of relying solely on the octet rule.